this, we're going to look at a limit amplituhedron today, and that's on joint work with my supervisor Rainer Stinn from the University of Leipzig. And I like to start this talk basically with the end, and that is showing the goal of today's talk, and that is basically, well, I usually say understanding the sentence, that is to say the limit amplituhedron, which I denote by A sub k infinity, which lives inside the Riemannian GRK, k plus 2, is a positive geometry. So, however, today is of course a bit different. We are all interested in the amplituhedron. Nick gave us a rough description of what a positive geometry is just like an hour ago. And then really only the thing that I have to explain to you guys is what I mean by this limit. And then yesterday I was talking to some of you guys, and I was assured that we vividly remember Yaros and Nima's original paper on the amplituhedron. And then I'm very excited to have physicists here. You've seen this object, and it's in fact just a master amplituhedron, and that is like in one of the later chapters of the original paper. And today I want to convince you that this special case, which we call limit amplituhedron of the master amplituhedron, is a positive geometry. And here is one. Well, in fact, it's more or less the only one I can draw. The other one, well, we have now a new conjecture, but I'm getting ahead of myself. So, well, in fact, it is our very much beloved pizza slice, in a way. And the green shaded part, A sub 1 infinity, is the limit amplituhedron for k equals 1, and is bounded by a circle and an additional line, basically. And you can see there are some polygons in here, which is the guiding visualization of what the limit process really should be. All right. So even though we certainly know what the amplituhedron is, I'm going to fix notation later on in the talk, but certainly what I want to do is to talk about positive geometries for quite some time, to develop a notion of adjoints, basically, which is, in a way, a Leipzig way of thinking about positive geometries in economical forms.
Sorry, what is the universe plus?
Oh, sorry, yes, okay, so usually I advertise the Universe Plus project, which I'm associated to, and we study positive geometries in this Universe Plus project. So if you like what you see, it's a good thing to see what else we are up to, and maybe you can get involved. And before I start diving into the notions, well, this whole limit amplituhedron story is also going to be a story about rational normal curves. If you're mathematicians, you might be inclined to liking those. They are nice curves, and maybe you appreciate that side of the story a bit more. Well, so we're going to start with positive geometries, and in fact we're going to start with a line segment and work our way towards the notion of an adjoint. And even as mathematicians, I shy away of writing down the whole definition of a positive geometry. It's quite a mouthful, and so I very much agree with Nick in saying, well, we really want to think of a variety and a semi-algebraic set inside the variety, or its real points. And the interesting part is the top-dimensional differential form associated to it, which has some additional recursive property, as Nick was describing. And we're going to see this with the recursive property and how we think about it, basically. So, of course, in 0 dimension there's just the point, there's not as much interest. So actually let's look at one example, which is the line segment here in blue, denoted by L, and has two boundaries, the red point A and the turquoise point B, and it sits inside the one-dimensional projective complex line, and I've only drawn the real points here. So this is all a real picture, but you think of the variety actually as a complex variety. And the important part are really the boundaries. So of course then you guys seen canonical form for this, like a couple of times, I imagine at least. but I want to put your attention towards the function in front of it, where the denominator really just recalls the pole structure along the boundaries of our geometry, and then the numerator is what we are mostly interested in our style of thinking about it. And I'm going to say how to get the numerator in just a second, in these cases at least. So, okay, that is just, I think, a side note for us. How do we relate this one-dimensional positive geometry to the zero-dimensional? Well, we're taking the residues. Nick was talking about this. They're basically along the boundaries. And if we do this, then you see that we're going to recover for the boundary point B, for example, we're going to recover precisely the canonical form of that point, which is the plus one. This is how the recursive properties of the canonical forms work. And here, I want to step it up to 2 dimensions now, where the first time something interesting appears in the numerator, really. And this example is going to be our quadrilateral cube, the negotiated area here. And we're going to go through all the parts of this picture step by step to see what this turquoise line is going to be in just a second. So, for us, the most important part of these pictures is the algebraic boundaries. So these are precisely the hyperplanes. So this is inside a P2. So these are lines cutting out our polytope. And the extension of these lines in the whole plane are then these dotted things, and they are labeled by the equations. And we call this the algebraic boundary. Well, it's just the product of all the polynomials. That is the union of the lines. We call algebraic boundary, well, with an abuse of notation, it's really the polynomial writing down, but I'm thinking of it when it vanishes. Right. So, the first notion we introduce here, which is going to be important for us, is that of the residual arrangement. And this is part of the singular locus of our algebraic boundary, which does not intersect the semi-algebraic set we are interested in, that is the quadrilateral cube. So in our case, well, if you've taken a course in algebraic geometry, at some point you will always know the singular locus is certainly, or contributions certainly come from intersections of lines. So every intersection of these lines might be in the singular locus of the algebraic boundary. And then, well, there are exactly these 4, but those 4 intersection of lines are actually vertices of our quadrilateral, so we don't care for this, for the residual arrangement. And the only other 2 singularities of our union of lines is the point P1 and P2 in turquoise here. So that's our residual arrangement. And then we want the notion of the adjoint. And the adjoint is the polynomial of lowest degree, which interpolates precisely all points that lie in our residual arrangement. So for us here in the example, so it's just going to be a line. And this line equation is going to be given by this polynomial here. And that's going to be the adjoint. It's going to play a crucial role for us to understand positive geometries. So, if you like fancy math language, so of course saying lowest degree is a bit vague. So what this degree is really determined by is by looking at the canonical divisor of the degree of it, which is, this lives inside the P2, and in general these things might live in a Pn, and then it's going to be the degree associated to this is going to be -2 here, and then you look on how what the degree is of our boundary divisor, that is 1 degree here, 1 degree here, 1 degree here, it's degree 4, and then you add those numbers together and subtract 1, so that's like 4 minus 2 minus 1. This gives you 1 dimension, like a 1 degree polynomial, so a line. Yes?
I have a very naive question just about the definition. What is a singular locus?
Well, okay, so in principle the singular locus is defined by looking at the tangent space of a variety. So, I mean, in planes you can really, if you do plane geometry, everything that intersects basically is going to be part of the singular locus. The notion, like, in more generality, is a bit more involved.
Okay. So in this specific case, the singular locus is the intersections of these lines. Okay. Good.
Yeah, and that's very true. All right. So what's the idea behind the adjoint? Well, it's supposed to cancel the spurious poles outside of our positive geometries. And what do I mean by this explicitly? Well, I tell you, a good contender for the canonical form, well, in fact, the canonical form of this quadrilateral is you put the algebraic boundary equations in the denominator, same as before, and in the numerator of the function, you put the adjoint. And so, why does it cancel the poles? Well, if you restrict this function or differential to one of the facets, for example this one, then you see that the adjoint is chosen nicely such that one of the terms cancels and we're actually obtaining a canonical form for a line segment where previously our boundary points were minus a and minus b, and here this is minus 0 and minus 1. So this is the recursive property of positive geometries, explained by adjoints and residual arrangement. That's going to be a key ingredient of what I'm going to talk about later.
Is it always possible to find a joint, like explicit form of it in 2 dimensions? I can imagine it's easy, but beyond 2 dimensions?
Yeah, well, it's a bit tricky, yes, but it is true for every polytope, certainly. You can use this kind of reasoning.
Yeah, polytopes?
Yes, well, we're using the same notion even for non-polytopes, so yes, that's also doable, but yeah, that's...
Is there a prescriptive way of doing that? Some difficult examples?
Well, in a way, well, yes, in a way, and this is also what we do. We study the residual arrangement, that is understanding the singularity structure of whatever set you're interested in, basically. And then you actually need to find this adjoint, which is a computational problem, but can be reduced to linear algebra since you know the degree of the polynomial you're interested in. Yeah, but it's fairly tricky.
Is the choice of the adjoint always unique?
Pardon?
Is the choice of the adjoint always unique?
Yes. So up to sign, I think. Oh, okay. The choice of the adjoint is unique up to scaling by any multiple.
Sorry.
Go ahead. I have.
So this up to scaling. I mean, how do you get the correct normalization for omega?
Well, you actually need to compute residues at some point, or what we end up doing is you go. So if your residual arrangement or the boundary, the algebraic boundary is really nice, then you get connectedness, and then if you set one to be, you will always want to end up with the values at the 0 dimension, at the vertices, to be plus or minus 1, and then by connectedness, this tells you what coefficients to choose for the overall, what scaling to choose for the overall adjoint to make that work.
Okay, thank you.
I thought that even in 2 dimensions it's possible to construct, like if you take a line and a cubic curve, then that joint is not unique there, I think.
Yeah, okay, yes. Yeah. No, it's not a general statement.
Restrictions on the genus of the curve, on the boundary.
Yeah, very much so. That's true. Yeah, these things are called polypoles, for example. Yes, and you can mess them up like fairly easily, actually. Yeah. That's true. All right. So, this is the important notion for us. And then, okay, here's a slide. Of course, you've seen some positive geometries. If you believe this process I've described for this 2-dimensional polygon, then you might believe that every project convex polytopes is a positive geometry. Or you might, as Lara does, like positive parts of toric varieties. well, this is just advertising for some other projects inside the Universe Plus project. And well, this is a picture from Simon Tellen's webpage. Here's the toric variety, and which is the turquoise part, and the orange part is the positive part. This is going to be positive geometry as well. But I use this slide mostly to advertise this positive geometry in terms of mixed Hodge theory. There was a paper earlier this year by Brown and Dupont, and they put this whole framework of positive geometries, as we've known it, which originated from physics, and put this into a bit more abstract mixed Hodge theory sense. And well, I'm jumping again a bit here, but I'm hopeful that we, with Dimitri Pavlov and Rainer Sinn, we're going to use their more broader framework to shed a bit of light on some questions about the amplituhedron and related things. Yes. Okay, so let's see some notation for the amplituhedron. I'm going to choose Z to be a totally positive matrix of size n times k plus 2. So all of its k plus 2 times k plus 2 minus are positive. So that also means today I'm going to talk about the m equals 2 amplituhedron. If you know, otherwise we would have chosen this 2 to be maybe 4, maybe not 6. That's scary. So the non-negative Gaussian we denote by G greater or equal k of n. This is just the, as usual, just where all the Plückers in its Plücker embedding have the same sign. And then the amplituhedron map is denoted by Z tilde, and I just multiply, well, I think of my elements into Gaussian G k n as k times n matrices, and then this is just matrix multiplication as usual, by the left. And then I denote the image, that is the amplituhedron, the image of this map, where it's well defined. I denote by A sub k super n, and the dependence on the Z matrix is implicit for now, but it's going to play an important role when we move to the limit amplituhedron in just a second. Yeah, okay, so here's an example, but I mean, this is the silly example where I choose k equals to n, and this is really just an n-gon, so you've already seen an amplituhedron today on the blackboard, or on the screen. And, well, so I mentioned the following theorem by Christian Ranestedt, Rainer Sinn, and Simon Tellen from 2024, where they're shown for the m equals 2, k equals 2 amplituhedron. I use related ideas, certainly I use the ideas of adjoint and residual arrangement to prove that the amplituhedron is a positive geometry, which all of us believed at any rate. But this was really a starting point where this project took off, because they developed, in that paper they developed a notion that really helped us to understand what the master amplitude and limit amplitude should be. Well, okay. From this, so one of the tools that I need to introduce to you is that of Schlegel diagrams. So you consider a 3D cube, and the front facet is the one with the boundaries here put in red. And now you imagine, it's 1999, you're Harry Potter and you see the Nimbus 2000, whatever. Press your face flush up against that face, and what you're going to see, well, it's not the Nimbus 2000, but you're going to see the Schlegel diagram, which records just the facets incidences. And this is going to be the tool. Just look through one facet from really close up, and we're not going to do this for the cube, but rather from the cyclic polytope, for the cyclic polytope. So for me, the cyclic polytope is, in d-dimensional complex space. I choose n vertices of the on the moment curve and take their convex solve. That's the cyclic polytope for me. The moment curve is labeled by gamma d. And then the Schlegel diagram for 6 vertices on the moment curve in NP3 or C3, where I fixed the first point to be the 0 point in the moment map, and the 6th point to be the O1 point in the moment map. And I look through the facet where one of the edges is 1, 6. And then you can see all of these triangular facets of the cyclic polytope as depicted. And this is going to be a very visual tool to understand what's going on. Okay. So how are we going to use this idea? Well, so there's a way of understanding the amplitude as a semi-algebraic set by thinking about it, by thinking of points inside it as how they intersect the cyclic polytope I just shown you. And I'm going to go through an example with you. So we say n equals 6, so it's the same picture in general, and k equals 2, so this amplitude is in Grassmannian GR24. So points in the Grassmannian GR24 for me are lines, such as the orange one. And I claim the orange one is a point in the amplituhedron, so it characterizes in fact all points of the amplituhedron. And how should you read this picture? Well, so a line, the orange one, is inside the amplituhedron if it enters in this diagram, if it enters the facets, facet 1, 3, 4, and exits a facet of the cyclic polytope, which is lower in this diagram. So one labeled by 6, 5, and 4 in this case. So what do I mean by enters and exits? It is a line, it doesn't really have an orientation. I really just mean the one that it enters is the one which has the 1 as one of the vertices, and the exit facet is going to be the one which has the 6 as the facet.
Is it possible to cross as a 1, 5, 6?
Yes, so this one is a bit more special because I fixed this point, but in principle, yes.
But then when would you enter or exit in that case?
Yeah, so this isn't. You need to. This one needs to be carried out a bit more carefully. I'm not claiming this at the moment. It's easy to see what to do with this, and it's really just a visualization tool for here, for the purposes of the talk. So, but there's a bit more special case of the same thing. So. A point still in the interior of the amplituhedron could also be such a red line where, okay, so they now enter through, the line steps the cyclic polytope in a facet, 2 facets of the cyclic polytope which share an edge, the edge 3, 4. And this line still might be in the amplituhedron if the projection from the intersection point of the line with the facet 1, 3, 4 up to the edge 3, 4 is higher up than the same projection of the intersection point from 6 onto the same edge of the intersection point where the line exits it. It's just like, it's basically the same, same idea as the first one, but just a bit more nuanced. And so, this was a tool basically developed by the authors of the paper I've just shown you the theorem of, and it's going to be useful for us in just a second. All right. So we can finally take things to infinity, and we're going to do so by introducing a notion of partitions, which is going to be helpful for us. So for us, an partition as a sequence of length n, if it's like labeled by sub n, of the real interval 0 to 1. And we always fix the first part of the sequence, increasing sequence, to be the 0, and the nth part, the last part, to be 1. That is just a choice we make, but it helps us organize all of our computations later on. And then, okay, as usual, so my notation for the moment curve for degree k plus 1, rational normal curve is just 1 through up to t to the k plus 1. And here is now a key ingredient. Well, so for each such partition, we then define a matrix, which is an n times k plus 2 by just stacking n points on the moment curve on top of each other. These are tuples, of length k plus 2. So this is really, if I stack n of them on top of each other, this is really a matrix n times k plus 2. And since this is a van der Monde matrix, this is actually a totally positive matrix, so we can use this to define the amplituhedron. And this amplituhedron then is denoted by a sub k to the I. And now the dependence on the Z matrix is more or less explicit in our notation, so this is important for us. Well, okay, and finally there we are. So the limit amplituhedron, ak infinity, you should think of as the union for all partitions of the interval 0 to 1, increasing partitions, and then you just take the union of all of these associated amplituhedrons to that Z matrix defined for any partition. Yes? So this is a priori, oh yeah?
Does this end up being smaller than if you took a union over all possible Z matrices, or does it somehow match that result?
No, I don't know for sure, but I imagine that to be smaller. This is much more...
Yeah, I would imagine it to be smaller since you're specifying, it's much more constrained.
Yes.
Okay.
Yeah, that is certainly true. And what do I want to say? Well, it's still, this union here, I just write it about for all I, but this is really a union for uncountably many things. So it's not even clear what this object should be, but we want it to be a semi-algebraic set. And but this does not, from this definition, it does not immediately follow that it is going to be in semi-algebraic sets. But since we find its algebraic boundary later on, it's a nice set. However, still, for the more mathematically inclined readers, another way of thinking this, a bit more rigorous, is that you take the direct limit and for the category of topological spaces, where you refine the order with respect to the refining order on partitions. So a partition is a subset of the other one, then it is smaller than the other one. Okay, and that's the same set. But really, geometric intuition is to just stick lots of amplitudes together. Okay, so we started by understanding positive geometries through their boundaries, and so we are interested in finding out what the boundaries of this limit amplituhedron is, and this is where our Schlegel diagrams come in. So here's again an example where we fixed n equals 6, so there are only 6 points on the moment curve, and this is our cyclic polytope. And in fact, from this description, then also it follows that boundary lines, so that are the boundary of the usual amplituhedron for that choice of that matrix, these can be lines which go through the edge of a cyclic polytope. So that's a more special version of the same picture I've shown you before, where we just push the line to the edge and it does not enter or exit any interior of the facets. Actually, it's actually on the boundary of the facets. That is to say, the edge. And okay, even more special, and then it turns out these should be the boundary lines of the limit amplituhedron is, well, if this line actually goes through the vertex of our cyclic polytope. So then just remember the vertex of our cyclic polytope, because the cyclic polytope was chosen as the convex hull of points on the moment curve, is actually a point on the moment curve. So this line meets the moment curve.
Can I ask about this picture? So are those all possible boundaries, or just the ones which are 1, 6, I plus 1?
No, again, I don't think these are all possible boundaries. Yeah.
So that right here, the bracket 1, 6.
Yeah, it's like this one is again different. Yes. Okay. So now I claim these are precisely boundary lines of our limit amplituhedron. But in fact, of course, this is only for one choice of Z matrix. So what happens if you take, as I said, we should, the union of our amplitude. Well, we're going to get the following proposition. Points in the Euclidean boundary, that's like really the bounded region of our semi-algebraic set, are precisely the k-planes which intersect the rational normal curve, ck plus 1, in the interval yk plus 1, so that is in the interval that is parameterized by our choice of the interval of the rational normal curve of degree k plus 1, or mouthful, or there again, this is the special line you're pointing out basically, because we always fixed our interval to be 0 and 1 and our partitions to contain the point 0 and 1, so we might as well meet this point as well. I mean this line, sorry. Okay, and that is already very good. So understanding the actual Euclidean boundary of our semi-algebraic set was very good for us. Then what this really tells us what we like to have as the algebraic boundary of our semi-algebraic set. It should be just a generalization of this proposition, and in fact it will be. Okay, so I need to introduce one more notion for you though, and I'm not going to do this in a very rigorous way here, but the notion we need is that of...
Where's the second line segment 0, 1 coming from?
Okay, sorry, that is very good. So, okay, I mean, I go all the way back. I choose basically every partition of the 0 and 1 interval, but I do fix for every such partition the 0 point and the endpoint to be the 1 point. So if you plug this into the Z matrices, then the first row is always going to be 1, 0, 0, 0, 0, and the nth row is going to be 1, 1, 1, 1, 1. So in this picture, whatever amplituhedron I draw, the labels of the points will not change if I don't let n grow, but this line is always going to be the same. So the 1n line is always going to be the line spanned by like 1, 0, 0 up to k plus 1 and 1, 1, 1, 1, 1. So this is notation I fix. So this is the notation. Think of this as the 0 point under my moment curve and the 1 point over my moment curve. So exactly these points.
For me, this is a big question, but the amplituhedron emits a cyclic symmetry, and it seems like your construction is breaking that symmetry kind of from n to 1. Is there...
Well, no, I still want this to read cyclically though at the end. And if I were to write down the twistors and all of this, I also want to think about like n plus 1 being the same as n 1 twister.
Okay.
Yeah, I just fix, I mean, if I were to write down any amplituhedron, I would always, explicitly, I would always fix the Z matrix right first. And I'm saying just, okay, we study, a subset of these Z matrices in a way.
Okay. Maybe a related question. So the rational normal curve, you can think of as a curve on P1. Like, can you, instead of fixing it on 0, 1, can you work with P1 and take a limit? Does that make any sense?
So, how do you think of your rational normal curve? Sorry. Right. So from
as a curve from P1 to Pk plus 1.
Yeah. Okay. Well, we always pick an actual parameterization which goes from like C1 to an affine open on the Pk plus 1.
Okay.
Yeah.
Okay.
So, but in principle, this should be easy to projectivize. Well, actually, I'm going to end the slide on a slide which is very recent development, as by like a week and a half ago, which should tie in with that comment. I'm going to mention this later on. Yeah. Okay, so Yes, Chow hypersurfaces. Okay, I want to introduce this notion of a Chow hypersurface, and well, as I said, this really just the Chow hypersurface of the rational normal curve ck plus 1, as I said, just keeps track of all the k-spaces intersecting our rational normal curve ck plus 1. That is what it is, and then there's this Chow. It's a Chow hypersurface because you can encode this data in one polynomial, and the vanishing locus is going to be a Chow hypersurface. Here's an example, not for the rational normal curve, but it's the easiest one I think to think about. Well, I think of my lines in P3. So what I really do is think of my lines as an element in the Riemannian GR24. That is to say, I think of my lines as a 2x4 matrix in this case. I'm offering 2. And then encoding when other lines L prime meet L, well, this is just encoded in the equality when the determinant of 4x4 matrix, L, the 2x4 matrix on top of the other 2x4 matrix, so it's 4x4 matrix. If that rank is not 4, that is when its determinant vanishes, then these lines meet, they share a point, that is to say, that's this linear algebra. And if you choose points in the Plücker embedding, coordinates, so you choose the coordinates in the Plücker embedding for our line L, and it's just nice to see we can use, well, when I was still a physicist, I called this Laplace expansion, now I call it growth vector expansion. Whatever you do with this 4x4 matrix, you can see that if the Plückers, you denote by P12, then this is really a linear constraint in the Plückers of the line. So it's a hyperplane section, if you like these words, of the Riemannian GR24. So that's what the Chow hypersurface is, and then we generalize this to the rational normal curve. Okay, so as a reminder, the Euclidean boundary I call by partial AK super n, and that's just, you take the whole semi-algebraic set and remove its interior. And the algebraic boundary is taking that Euclidean boundary and closing it up in the risky topology inside the convex Riemannian. Okay. So, and then as promised, one of the main theorems for us is that the algebraic boundary of the limit amplituhedron, or the master amplituhedron, is really just the Chow hypersurface of the rational normal curve of the corresponding degree k plus 1, and the Chow hypersurface of this special line, and the secant line. And here I hope I'm going to convince you that this line is actually important for us to find a positive geometry. Here's the first example, which I've shown you on the first slide. So first of all, I removed these n-gons in here, but really what these n-gons were, where I choose points on the rational normal curve of degree 2, which is just a circle, more or less. So and if I choose, let n go to infinity, I'm just inscribing a half-disk. So that is what was meant here. So this is how you get the half-disk as the limit amplituhedron. And then if I were to remove this line and not include this in here, then this in itself is not a positive geometry. It doesn't even have boundaries, as Yara likes to point out to me. So we threw in this line to make it a half pizza, and it's a positive geometry because of this additional line. Well, in fact, because the vertices of this positive geometry, that is, we want to go down to zero-dimensional sets, are precisely the intersection points. So, okay. In my notation, C2 is that circle, or the rational normal curve of degree 2. Gamma is my moment curve parametrization. And here, again, this is basically what I've written down explicitly, because we fixed the end points of our interval to be 0 and 1. We have the secant line here, which is exactly S sub 0, 1. And in fact, so I've drawn you a real picture. So, I'm going to say this in just a second. So, And then, well, the observation was for the pizza geometry is that the residual arrangement, which again is the singular locus, that is the intersection points in this plane, they which do not intersect the semi-algebraic set. For a degree 2 polynomial or its vanishing locus and a degree 1 polynomial, they meet in 2 points, sorry. And these 2 points we can see here. So in fact we know that the residual arrangement for the limit amplitude is empty, which tells us that the canonical form is really just given by the Chow form of the circle and the Chow form of the secant line. This is what I said, right? This is what the main theorem of us says, and then just to square this up with what was known for the pizza geometry beforehand is, well, so I think it's in the 2017 paper on positive geometries, they looked at this half pizza and they triangulated it, take the limit for the triangulations and compute the positive geometries, the canonical form through that limiting process of triangulation. And they find that it is actually given, by this circle and line. So this nicely matches with what was found there. And really just to make sense of this and explicitly is, well, since we're in the plane case, there's some self-duality going on. So here in this theorem I claim it's like the Chow form and the Chow form of the line. But really what I do is I identify points in like dual Grossmanian with the same P2 my rational normal curve lives in and the secant line. So in this case, since we're talking about codimension 2 spaces meeting the same thing, they only meet them if the points are actually on the curves. That is to say, I identified the Chow forms with the curve and the line. All right. Okay, so we are near the end of this talk, but I want to go through one example higher up, and that's the k equals 2 limit amplituhedron. And now, instead of having a circle as the boundary curve, it's really the twisted cubic MP3. And we have, again, these two irreducible components of the algebraic boundary. And one first observation is, so the goal of having the algebraic boundary is then to understand its residual arrangements or its singular locus and go down all the way to dimension 0 to understand the residues. So the first observation is that the Chow hypersurface here is of dimension 3. I want to briefly talk about how you can see to do this, because it's a nice classical algebraic tool, and this is basically the main tool we use to prove everything in our paper. So if you understand this, then you can follow through our paper. So, and that tool is called incidence varieties, and in fact it just keeps track of when things intersect. So this is called sigma, and for us, we're going to set up the incidence varieties for points P, which are on the rational normal curve, or twisted cubic, and lines inside G up to 4. And we want to keep only those tuples where the point is actually on the line and also on the twisted cubic. That is when the twisted cubic and the line meet. So then what you would do is, well, okay, you fix one of such intersection points and project away of that point, and then you're really only interested in lines which contain a given point. And if you do the analysis of that, that's really just a two-dimensional subset. You lift this up to your incidence variety, and since the rational normal curve is a curve, so of dimension 1, you add 2 plus 1, which makes 3. So this is the main tool. And this allows us to really understand the stratification of the boundary of this limit amplituhedron in more general. For any k, here we're going to do this for k equals 2 briefly. So the first part is that the singular locus are actually secant lines of the twisted cubic. So that is a good other thing to keep in mind. Singular locus, singular points of varieties tend to be those which are a bit more special than, you know, your run-of-the-middle point of the variety. So usually a line would meet twisted cubic in 1 point maybe, and then it's more special if the line meets it in 2 points, which is the secant line. So it's part of the singular locus. There are other two-dimensional strata. So because we always fix the 0 point and the 1 point, lines that contain this point meet this secant line, because that's the line that goes through there. And since that point is also on the twisted cubic, they are more special. So you get lines containing the 0 point, lines containing the 1 point, and then like the generic behavior of lines meeting the twisted cubic and the special line. So that's really, there's lots of combinatorial works involved to make all of these computations work out nicely. And then we could go down in dimension 1. And you can see, okay, well, you can be even more special. You can contain the 0 point and still be a secant to the twisted cubic, or contain the other point. And then there's like something new that appears, and that is the only other ingredient from what you've not seen so far, which appears in like an any K. And that is, they meet like another new line, L01. And this line is written here as an element of GR24. So you see this is the all 1 point again. And then this point, does anyone see where this would appear in the parametrization of the moment curve? Well, it is the tangent vector at the origin of, you know, our chosen parametrization. And similarly, this is the tangent vector at the all 1 points in our parametrization, and this of course is the 0, 1. So what I'm going to say is that because we're interested in the singularity structure, and I was saying, okay, it's basically studied of tangent spaces, the tangent spaces, tangent vectors are going to appear, and they're going to be important in general. Going to be very helpful too.
Sorry, why is 1100 the tangent vector at the origin?
1100, I'm just like do the derivative of 1t squared t cubed and plug 0 in. That's what I want to say.
Why is the first coordinate 1?
Oh, okay, sorry. Yeah, this is because implicitly I'm considering only these three and put them in the affine patch of my projective space. Okay, yes, sorry. It's like I fluently switch between the affine patch of the projective space and the fullest point in the projective space. Yeah. It's the same, yeah. This one then is also explained. It's the only one. Very good. And so in fact, the vertices of our limit amplitude for k equals 2 is the secant line itself, which is just the, you know, it's the point in the Riemann to 4. It is in fact the tangent line at the 0 point, and it's also the tangent line or tangent vector, depending on how you want to think about it, at the or 1 point. Okay. So, and now the only thing that really needs to be proving is we found that for the pizza, the residual arrangement is empty, and for like these more fancy reasons, we also know that the adjoint should be polynomial of degree 0. So we really would like the residual arrangement to be empty. And this is our goal, and I can convince you basically that this is also not too bad. So what we really show is that for each of the strata I've shown you, we can actually parameterize points in the amplituhedron which make up a dense set in that stratum. Here's an example of that. Well, if you're interested in this is one of the simplest ones, but if you're interested in secants of the twisted cubic going through the 0 point, then you might look at the following set here, which is one-dimensional. This is a one-dimensional strata. So you just put the all 0 point in here, again on an alpha patch, and then any point on the twisted cubic, making this any point in this subset is actually secant going through this. This is the naive parameterization of what you want to do. And then you just build the correct points in the amplituhedron by choosing your partitions nicely. So you take an n times, 4 matrix. And the first point is always the 1, 0, 0 point. Last point is always the 1, 1, 1 point. And then somewhere in here, in the ith row or whatever, you have the S1 S squared S cubed. And now you choose a point in the non-negative Gaussian simply by having a 1 in the first row and first column, and the 1 in the second row and in the ith column. So if you are now multiplying these two things, because that is certainly in the non-negative Gaussian, so you can apply the Amplituhedron map, and then this is just matrix multiplication. This gives you exactly 1 point of this form. And so what you end up doing is for any S, you can choose such a matrix, making up a one-dimensional stratum, and you parameterize these guys. And this then shows you that your limit Amplituhedron is always intersects all of our strata densely, so the residual arrangement is empty, and you know how to compute the canonical form, basically. So, let's not go through all of this. I've never intended to do so. This is just that I've shown you how to do this for k equals 2, basically. For any k, you've already seen all the ingredients. You just need to combinatorially organize how to structure the computations. In general, osculant planes are going to appear, that is taking higher derivatives at some point and looking at the span of these higher derivatives. But you can organize them as such, basically, which then ends in the theorem I've shown you in the very beginning of this talk, stating that the residual, well, first of all, stating that the residual arrangement is empty, and then our limit Amplituhedron or master Amplituhedron is actually positive geometry, and this is the canonical form. These are coordinates on the Gaussian G2K. That is given by 1, plus minus 1. And the canonical the Chow forms associated to the twisted version of the curve, and the secant line. Very well. So that's the main work we've done so far. And there's some words to say on m equals 4 Amplituhedron and other ways where we can take it. But very recently, coming back to one of your earlier questions, I think, well, we have, at the very least, we have a conjecture, but one part might, we might actually prove very soon. And that has to do with hyperbolicity. So that is a topic mathematicians like very much in the past, and Ian Lear liked a few weeks ago. So the conjecture is as such, well, the limit Amplituhedron coincides with the hyperbolicity region of the rational normal curve of degree k plus 1 with respect to some secant line that we've chosen. And so mathematicians have been excited about hyperbolicity. What does that really mean in our case here? Because I haven't told you what we should think of. Well, you've seen the pizza now a couple of times. The only thing that is really special about this pizza is that you can see the intersection points of your line with the conic in the real points of your projective space, which is a priori complex. And so in fact, being hyperbolic really just means that you choose a point inside the circle, and then any line through that point will intersect the circle in 2 real points. So, of course, if you just take the circle in general, then any point inside this circle will have this property. But that didn't make a positive geometry. So we needed to divide the circle by a half space with that sad line. And that is why there's a subsense with respect to another secant line, which really singles out either this or, of course, symmetrically the other guy. So that is to say, in general, we expect this for the twisted cubic. So the best visualization we probably have is think of the circle, or for k equals 2, think of the twisted cubic, and think of a convex hull of the twisted cubic, and that's going to be the limit Amplituhedron. And Mario Kuma recently had another connection generalizing this in general. Maybe all hyperbolicity regions, if you care about them, might be positive geometries. And I don't know if physics would be interested in these kind of, if they are positive geometries, but it's certainly a nice positivity constraint. All right, that's about it.
Thank you very much for a beautiful talk. Are there any questions?
So usually for the Amplituhedron, we think that the Combinatorics is independent of your choice of Z matrix, but here it seems the avatar of the moment curve is very important.
Yes.
Do you think that some different choice of positive matrices, well, that looks the same, similar, completely different?
Yeah, you're asking something very good, and we already had some debates about it. So, like relating back to what Artem asked earlier, is of course in principle, like having any totally positive matrix might make this thing bigger then, right? And I don't think I can claim anything about it, but for your question explicitly, this is how we got thinking about hyperbolicity in the first place, because I was bothered by, okay, do we really need to take the rational normal curve, right? Can we do something a bit more general? And this hyperbolicity stuff, even if you might not have heard about it, this is certainly one way of generalizing it, and it might still be the very, very, very same pictures we would be drawing. So a hopeful yes, it might still be like somewhat independent of your choice. Yeah.
Can I ask a related concrete question? So if you replace the rational normal curve with a convex curve,
I don't know what the convex curve is.
So one way is like if you just take a sequence of points and stack them, that then you get a matrix with positive maximal minors.
Okay, I see. And that is called a convex curve.
Yeah.
Oh, okay. We haven't tried this. Let me ask you then afterwards what an explicit example would be. That would be
the rational.
The rational. Well, okay, yeah. Well, other than that.
Okay.
Yeah.
Maybe I'm misunderstanding, but if you let Z be arbitrary with positive maximal minors, then like you would get the entire gross minor k comma k plus 2, right? Because the GL k plus 2 just acts on those Z matrices, preserving positivity. So I think the question for just arbitrary taking the limit for all Z is just the entire
It's everything you think.
Yeah.
Ah, okay. All right. Thank you. Okay. Understand.
So what's known for m equals to 4?
Okay, so, this is one of my points on the agenda, talk to some of the combinatorialists and you guys. So I wasn't aware, one of the key points that made this possible is that the m equals 2 amplituhedron boundary and its algebraic boundary was well understood. And I wasn't aware that the work has been done for the m equals 4 amplituhedron as well. So there is the good description of the algebraic boundary, which allows us to do stratification. So I'm very hopeful to do this. We haven't started doing that then.
Is that boundary stratification completely known for m equals to 4? I think that it's not.
So the corollary I've seen in a 2025 paper that says that the Euclidean boundary, and I just want to take the Zariski closure of it, is really given by I plus 1 in the twistors and j plus 1. That's
the first boundary. So you just need the first boundary.
Okay, what's the first boundary?
I mean the codimension 1 boundary, but without.
Yes, okay, and then we would, this might be hard, but we of course intersect everything to go down. So this will be higher codimension.
What I'm saying, I think that this structure is not really known completely. I mean, it's known for this other object which is called momentum amplituhedron. That there it's known. But then,
maybe I'm a bit too rushed then.
There you are in trouble that the object itself lives in gross minor, which depends. The size of the gross minor depends on n, so it's very difficult to take limit.
Yes. Oh, okay. So you're thinking of it in the twistor embedding, basically. Where it's in GL.
No, so one-to-one amplitude lives in the space, which it's the product of two Grassmannians, but one of the Grassmannians, the size of it depends.
Oh,
on
I see. Okay.
And you can talk about this more.
Yeah, I would be very happy. And also, so I'm still somewhat optimistic about m equals 4 because we didn't need any other input than the codimension 1 boundary. So maybe this still works for m equals 4, even though the other ones
This
aren't.
one, no. Yes.
So let's take k equals 2. Yeah. K equals 2.
Yeah.
For example. Now, do you think that your result survives if you don't consider the full amplituhedron but just some slice? So you take the object, you say that, let's say, AB1 or Y13 is negative, and how does it change the result?
So you want to slice our limit of the master amplituhedron?
You just take the amplituhedron, you cut it in half.
Yes.
And would that still this piece? Would your result still apply to that or not? Because it still has, for n goes to infinity, it still has kind of infinite number of boundaries. You just take just piece of it. Yeah.
So is that the same as saying you want to slice this guy up at some point?
Yeah, does that correspond? Well, you have a new boundary. Yeah. So
Yeah.
So you have this kind of, let's say that you slice it with Y13. So now this is a boundary.
Yeah.
In the original amplituhedron, there was a piece where this bracket was positive, a piece where it was negative.
Yeah.
There is no restriction. So now if you slice it with this new boundary, it kind of looks similar. The object is just some small generalization.
Would you agree?
Yeah, it's a different form now. Yeah. With a new pole also. Yeah. Because you have this boundary.
So I'm not entirely sure. So I thought briefly about how to slice. One of the dreams, as I understood, of the master amplituhedron was actually slicing other amplituhedron out of the master amplituhedron in a way. Right? It should contain the other amplituhedron, right? And in a way, maybe I'm hopeful, but we haven't tried yet. To see if this works.
What is the definition of the infinite amplituhedron when you take the direct limit over all partitions?
Yes.
And I can expect you to pick one chain of partitions and just take its limit.
This is a chain of partitions, yeah.
You take all of partitions or just one chain?
Oh, well, no. I actually take all of them. Not necessarily one chain, and I add one, and I can also start with a new one and have one.
Yeah, but does it would they get a fundamentally different object? Okay.
No, I think so. The point is, you just will restrict. This direct limit is then ordered by only these chains which you can compare which one is the subsequence of the others. So implicitly I'm thinking always about one of them, but in principle you choose everyone.
Okay. Yeah. And also
the idea is really how do you inscribe n-gons in here, and you can do this in many ways, and then you can build up a chain of n-gons, right? But it doesn't matter.
Yeah. And also does this have some nice description in terms of twistors? A way to look at it in terms of twistors or no?
Yeah. So I tried to work with twistors at some point, but I couldn't. So the nice thing was that the formula for this guy, which you can basically write down in twistors, I think, they matched up nicely with what we find. Actually polynomials if you were to write them down, but I don't know how to do this in general for the formulas for amplituhedron, then take the limit and see that this is actually a nice polynomial. So there's some work to be done on this.
Any more questions?
Can I ask a question? So Have you looked at the m equals 1 case?
No, we haven't looked at the n equals 1 case. So the m equals 1 case is basically hyperplane arrangement, is that true?
Mm-hmm.
Yeah, I haven't yet.
I don't know how that matches out. So it might be interesting to use.
Yeah, I mean, one interesting thing is that for the m equals 1 amplituhedron, it's not positively convex. So the canonical form is, or the canonical rational function can change sign on the interior of the space. So.
I think the hope is that these limit amplitude in general might be convex regions. So, yeah, but
Maybe not for auto.
yeah, okay, that's also true. All right.
Okay, there are no more questions. Let's thank Jonas again. And the next